Okay, just a short lecture on cross ratios, which is chapter 3C in our text. And I'm probably only going to get through about half of this chapter. I'm going to finish it on Monday. So what we have in store for the whole chapter is I want to define what a cross ratio is and then talk about points in perspective from P. And then I want to start, to talk about a cross ratio theorem. And that theorem is the one that we'll end on today. So we'll try to get through 1, 2, and part of 3. And then I'll finish up the rest 3 and 4 on Monday. So what is a cross ratio? I mean, first of all, just to give you a sense of what it is, a cross ratio is a number that's associated with a set of 4 distinct collinear points. That is 4 points on a common line. So one way you can kind of think of it is it's a way to characterize how far apart or close together 4 collinear points are without appealing to any metric system. In other words, without using a ruler. If you kind of think about this, you can do this for 2 points as well. You could say, what ratio the distance from A to B is compared to B to C if they're collinear. And you can do it with 3 as well by different ways of thinking about how to compare those distances as ratios. But it turns out that the 4 points is really important in cross ratios in a certain setting, and we'll see why that is. So let's go ahead and define it. So if we have 4 distinct points, A, B, C, and D, then the cross ratio of the 4 points written CR, A, comma B, comma C, comma D, is given by this quantity. It's a ratio, and you can see it's A to C times the distance B to D over the distance A to D times the distance B to C. So if these 4 points are, on a line like this, you can kind of think of it like this, A, B, C, and D. Then on top, on the top rate of the fraction, you can kind of think of it as this one and this one over what's on bottom, which is A to D, which would be this one and this one. And I guess you can kind of see why they're called cross ratios. There's sort of this crossing that happens on top, and then I guess non-crossing on bottom. But this would be sort of a way of sort of assigning a number to the spacing between 4 points that are collinear. Okay, so that's, this bizarre sort of thing called a cross ratio. Let's go ahead and practice a little bit with it. Let's just explore the concept and suppose that the points A, B, C, and D are equally spaced along a line. And for each, let's find each of the following. So I'm going to go ahead and copy this. And throw it on the next page so that we have it sitting there. Okay, so let's see. We've got 4 equally spaced points. So I'll just sort of draw that out here. Well, I guess the picture could look something like this. A, B, C, and D, 4 equally spaced points that are all collinear. So we can kind of think of like these are all equally spaced. And what we're supposed to do, one is find CR, A, B, C, D, which we know then to be AC times BD all over AB times BC. So if we kind of assign a metric, let's say it's a unit between A and B, then the distance between A and C we could kind of think of as 2 units. The distance between B and D we can think of as 2 units. The distance between A and D we can think of as 3 units. And the distance between B and C we can think of as 1. So 4/3 is the cross ratio if we take the points in order A, B, C, and D. But what if we switch up order? And what happens if we do D, C, B, A? So the cross ratio of those 4 points. Let's see, so we would have DB times CA crossed part on top, and then outsides and insides on the bottom, so it would be DA times CB. So let's see, DB is going to be 2, CA is going to be 2, DA is going to be 3, and CB is going to be 1, so we get the same thing, 4/3. So it appears that cross ratios are order left to right, front to back, doesn't appear to affect the value of a cross ratio. But let's see if we take things out of order. So the last one is B comma A comma C comma D. Let's see, so this would be, again, the cross ratios would be BC on top times AD all over on bottom, the outsides, BD times the insides, AC. So let's see, BC is going to be 2, AD, wait. BC is not going to be 2. If I come back up here and look, BC is that distance now, so that distance is 1. And let's see, AD is going to be 3. And on bottom, let's see, we'd have BD, which is going to be 2 times AC, which is going to be 2. So here we get 3/4. So it does appear that cross ratios, order is important. I guess in the naming of the points, you do get a different cross ratio, even if you use the same collection of points in a different order. So I guess that's the little lesson we learned here, just applying the definition to, a set of points on a line that are equally spaced. Order, if we take them out of order, we get a different cross ratio. Okay, so here's this kind of fancy number we call a cross ratio, and what you'll learn in the chapter, and I would encourage you to read it. He does a really nice job introducing why cross ratios might be important. It's just a really nice sort of lead up to this part in the chapter. But it turns out that the real neat theorem about cross ratios has to do with projective geometry, and we don't really study projective geometry in this course, but if we did, this would be a foundational theorem. It turns out that we can use cross ratios to create a kind of a nicer proof of the butterfly theorem that we saw in the last lecture, and that's kind of his motivation. But it's also just a useful tool that we can use for other geometric purposes, and you'll see that in your homework this week. So what is a point in perspective? We say that sets of collinear points are in perspective from a point P if they look identical to an eye that's located at point P. So I think the best way to understand this is just to see a picture of what it means to be points in perspective. So here's the picture that I found on the internet that I like the most, and you have this person looking from a point, for your book this is point P, and what he'll do is instead of A prime, B prime, C prime, he'll call this W, X, Y, and Z, but it's the same idea. If somebody's looking at four collinear points from point P and say they belong to, let me get my highlighter up, they belong to this line. So these 4 points along this line, A, B, C, and D, would appear indistinguishable, right, to these 3 points that are along this other line. Let's say, these points are on line M, and these points are on line N. So the points on line M would be indistinguishable from the points along line N to the person whose eye is looking from point P. So that's what it means to be points in perspective, if they're indistinguishable from the point of view of the viewer. So I mean, it's kind of a vague definition, and so your author does a nice job of cleaning it up. But I wanted to give you that view first of all. Again, the idea is this, that collinear points, sets of collinear points, are in perspective from point P if they look identical to an eye that's located at point P. So the definition in general is more formal. So we can define points in perspective as follows. Suppose M and M are lines and P is a point not on either of them. Okay, so let's just sort of draw it out. M and N are lines. Say this is line M. Let's say this is line N. And P is a point not on either of them, so I'll put a point P right here. Okay. Then the points A, B, C, and D of line M, so I'll put them in here as A, B, C, and D, are in perspective from P with points W, X, Y, and Z of line N, respectively, if W, X, Y, and Z are on lines PA, PB, PC, and PD. Okay, so let's see what that means. If we're on PA, I didn't draw the line quite big enough, did I? So I guess I will. There's PB. There's PC. Here would be PD. Let's see, PA. I think I'm going to change where A is just because I can't quite get what I need there. Well, maybe I should do it this way. Why not? Just leave it as A. And we'll just extend the line N. Why not? So PA would look like this. So again, this is my line N. I know this is a little messy, but so it says if W, X, Y, and Z are on lines PA, PB, PC, and PD respectively. So this would have to be the point W then. This would have to be the point X. This would have to be the point Y, and this would have to be the point Z. So that's what it means to be in perspective. We say that A, B, C, and D are in perspective with W, X, Y, and Z if W, X, Y, and Z are on PA, PB, PC, and PD respectively. And again, these points are indistinguishable in terms of their spacing, I guess. If a viewer was viewing A, B, C, and D or W, X, Y, and Z from point P. So that's what it means to be in perspective. Hope that makes sense. And here's the big theorem. So the big theorem of this chapter is this, that suppose that A, B, C, and D are distinct collinear points in perspective from some point P with distinct collinear points W, X, Y, and Z respectively, then the two cross ratios are actually equal. And that's pretty astounding, right? That you would have, these points A, B, C, and D, which are spaced completely different than these points W, X, Y, and Z on their respective lines, but in effect, we can kind of think of them as the same in terms of this number, this special number called the cross ratio. And so you can kind of see how this, might be helpful. If you had sort of a ruler at M, you could kind of get a relative sense of their spacing by calculating the cross ratio, which would give you a relative sense of spacing of W, X, Y, and Z on their line, as its cross ratio would be the same. To really understand this, I think you need to play around with our GeoGebra technology. So what I've done on the Canvas page is to give you an applet that you can open up. I've already opened it in another screen, so in a browser, so I'm just going to go there right now. And so what I have here is just the setting of the cross ratios. We have A, B, C, and D. So it turns out that the way I have it built, you can grab this point B, and you can grab this point A, and you can move this point C, and you can move this point D. And what that does is then, it moves the point Z so that Z is always in perspective with D. It moves the point Y so the Y is always in perspective with C, and so on. But what is neat is that I can actually adjust X and Y on the blue line to see if we chose a different line. So X and Y define the blue dotted line, A and B define the red dotted line, and C and D are free points on, I guess, the red dotted line, and they determine X, Y, and Z. And what you see in the upper left is that the cross ratios for the two, which are calculated right there for us, do indeed remain equal. And this is perhaps not so surprising when we're in this configuration where we can see lots of similar triangles. But here's what's really crazy. If I drag this point X, let's say way out over here, so now we have sort of, let me drag X out, maybe that's easier. Now we have a situation where, where things are still in perspective. Do you notice this, that opposite A, I do indeed have W. opposite B I have X, opposite D I have Y, or C I have Y, and opposite D I have Z. But amazingly enough, the cross ratio remains the same. So in other words, we have a situation here where the cross ratio for WXYZ is they're out of order in a sense. They're not in the same order where it's WXYZ. We can see that X is now on the other side of Z and Y, and so even though it's on the other side, the cross ratios remain the same. It seems strange that we would call this perspective, but just remind yourself, what it means, right? W has to be online PA, and it is. X has to be online PB, and it is, and so on and so forth. Y has to be online CP, and Z has to be online PD. I'm having a hard time adjusting where these labels go, but I hope that you can see who's going where. So Y is the one that's on the left here, the black point on the left, and Z is the one on the right. So kind of an amazing result that no matter where we put these two lines and the points in perspective along those lines, that the two cross ratios remain absolutely the same. It's also interesting to note that the way that this is built, if we kind of dilate A closer or B closer or farther away from A, that the cross ratios remain equal in size. And the way that we really change the cross ratio is by manipulating C or D in this particular setting. So in a sense, the cross ratio is a proportional measurement. You can see that, like these are all in a sense proportional to one another, because all we're doing is sort of dilating A, B, C, and D. But if we change sort of the spacing in between A, B, C, and D, then the cross ratio does change. So in a sense, what the cross ratio is giving us some sort of a measure of, how these points are spaced relative to one another. Okay, so that's the big theorem for the chapter. And of course, where we would go next is to try to prove this. And I think what I'm going to do is just sort of give you some things to think about over the weekend, and then on Monday I'll ask you if you have some ideas about how we might go about proving it. Of course, you can also read your book if you'd like to know for sure. So let me just point a few things out about trying to prove this. So let's say we take kind of a standard looking cross ratio setting. Here's my point P. Here's my line, I guess, M. Here's my line, N. And we've got A, B, C, and D in perspective with W, X, Y, and Z. We're told the cross ratio of A, B, C, and D is AC, BD over AD, BC. And the cross ratio for W, X, Y, Z is WY, ZX, WZ over XY. And what we'd like to show is that these two things, these two quantities, are equal. And I guess the thing that sort of jumps off the page for me is the fact that, if we just kind of take a look at the first one, I'm going to use some highlighters here. I can see that AC seems to be, corresponding to WY. So if I kind of think about AC, here's AC and here's WY, and the thing that they have in common, of course, is this angle, right? So that's interesting, BD and XZ, so that would be sort of BD and XZ, and the thing they would have in common, of course, is this angle. So it kind of seems like angles have something to do with this. So, kind of the way I can kind of summarize this is that, if we can kind of look at, the first one, let's see, where do I want to put this? I'll put it right here. AC, we can kind of think of it that segment A to C, it's really the length of the segment, is somehow associated with the angle APC, which turns out to be associated with the angle or equal to the angle WPY, which seems to be associated to WY, right? So that's the blue piece, right? And likewise, we can say something like, well, if we're thinking about the length BD, then it's associated with this angle BPD, which is associated with the angle, XPZ, which is associated with the length XZ. And I shouldn't even say associated, it's equal to the angle XPD. And on bottom we can check it as well. Let's see, if we were to do AD, then that would be associated with the angle APD, which would be equal to the angle WPZ, which seems to be predictive of the length of WZ, or associated with the length WZ on the bottom of the fraction. And then I guess the last one to look at is that BC is, let's see, it would be associated with the angle BPC, which would be equal to the angle XPY, which seems to be associated with the length XY. So it seems like things work out like if we could somehow trade angles for lengths, then, this equality seems like it would make sense, right? So that's the first observation. But the real weird part about this is that, what if you change things? If we again take this as our line M, here's our line N, we choose our point P, and we let, W, X, Y, and Z be in perspective with A, B, C, and D. So if W is in perspective with A, then the line from, let's just sort of make sure everybody's with us, the line from A through P has to include W, right? And if X is in perspective with B, then, this line, let's see, if Y is in perspective with C, then Y has to be on the line PC. And I guess the last one, if Z is in perspective with D, then Z has to be on the line PD. So these are the three lines that, the four lines that connect the two sets of 4 points that are in perspective. So, in this setting, it just seems really unlikely that we're going to get something as clear as what we got above. But let's just see what happens. If we kind of look at the first piece here, again, kind of taking our intuition from the last page, if we look at AC, the first piece right here, we can see that AC is associated with this angle APC, which turns out to be what we're shooting for, is to get it associated with WY. So let's see, by vertical angles, I can see blue crosses yellow. We can say that that is equal to angle WPY, which seems like things are working out here, right? WY. So it seems like angles, again, if we can trade lengths of sides for sizes of angles, this seems to work so far. It turns out it only works for another one here if I take BC. So again, BC is associated with angle BPC, which is equal to angle, let's see, BPC is pink and yellow, so it would be XPY. And that's XY, which is, of course, that piece right there. But things kind of go haywire when we look at the other two angles. So let's do in red BD first. So if I look at BD, then BD is associated with this angle BPD. And if I was kind of to look at BPD, it doesn't seem like there's any particular, vertical angle, but you can kind of see what we're after. We're after xz. So xz is this one, and it looks like, the one that we just did was this one. It looks like what happens here is that we get supplementary angles, right? So it looks like angle BPD and angle XPZ is equal to 180, right? And in the last step, I guess, we'll do this one in, say, blue. If I take a look at AD, then AD is associated with APD. So I guess APD looks like that whole angle, right? And what we're after is an association with WZ, and it looks like WZ is this angle. So again, the same thing happens there. So it's plus WPZ equals 180. So, it doesn't quite work out the same, when things cross up. Instead of getting equal angles, what we get is we get some equal angles, like these ones, and other ones, right, where the angles, instead of being equal, they're just supplementary. So the question is like, how could we trade, equality for supplementariness, and somehow still maintain, some sort of equality? And the answer is this. It turns out that, that in all of these cases, since the sine of, of two supplementary angles, make this bigger, is always equal. That is, the sine of alpha is always equal to the sine of 180 degrees minus alpha. Then these two, examples show that the following seems to always be true for angles associated with cross ratio. And I guess that's that the sine of angle APC is always going to be the sine of angle WPY. And what the sine of, this is sort of our AC, and this would be our WY. This is our BD, sine of angle BPC would be equal to the sine of angle, BPD, would be the same as ZPX. So ZX seems to be associated with that. And then on the bottom, I guess we have AD associated with the sine of angle APD, and that would be equal to the sine of the angle. So AD, WX, WZ, WPZ, so WZ. And I guess the last one is the two middle ones. BC is associated with the sine of angle y. So again, the arrows are sort of the association that I'm trying to draw. And so I guess what I'm trying to say, and the other thing I should make clear is that we only looked at two configurations. One where A, B, C were on one side of the intersection of line M and N, and D was on the other, which switched the order of W, X, Y, Z on line N. And one where they both were on one side of the intersection of line M and N. But if you draw several other configurations, what ends up happening is you get some that are equal like this and some that are supplementary in all cases. So we haven't really evaluated all of them, but if you take a look exhaustively, you will find that either they're equal or they're supplementary in all cases. So I guess it comes down to this, that if we can show that the cross ratio of A, comma B, comma C, comma D, which we know to be equal to, let's see, it would be what, AC times BD all over AD times BC. If we can show that that's the same thing as, hope I've given myself enough space, I think I did, the sine of the angle associated with AC, that's angle APC, times the sine of the angle associated with BD, so that would be angle BPD, over the sine of the angle associated with AD, so that would be angle APD, times the sine of the angle associated with BC, so that would be angle BPC. If we can show this, in particular, this equality, this one is by definition, and this one is this provable? But if it's provable, then we're pretty certain that we would be done, because of the fact that these angles that are on the left, if I kind of think of them, if I draw, I guess, what's going on here? There we go. If I can show that these guys are the same as the cross ratio, then what's going on? I've got something strange going on with my machine. Try this again. Except for I want to do green. There we go. Well, that's blue. Here we go. These ones in green are the same as these ones in green. If those ones are equal to these ones in yellow, and then these ones in yellow would be, associated with these ones in yellow, we could say the cross ratio on the left would be equal to the cross ratio on the right. I hope that makes sense. So really it comes down to, can we trade out segments for sines of angles in the cross ratio argument? And if we can, based on our analysis above, then we could say that our proof is done, right? That these two cross ratios would have to then, these two cross ratios, that one being in green, this one being in yellow, these two cross ratios would have to then be equal. So that's the point where I think I'm going to leave you tonight. How in the world could we do this? I mean, if we kind of think about what's going on for this setting, what you're really going to want to think about is you're going to want to think about the setting where you have a line, where you have points A, B, C, and D on that line. We have some point we call a perspective point connecting each one of them. P. And, the big question is, well, how could we get to this spot? And I will give you just a big hint if you want to think about it and turn it around in your head over the weekend. The proof of this thing we're trying to get, right, relies on calculating the areas of triangles using two different methods. So what I would probably tell you to do is to think about how can you calculate the area of APC. Let's do that one first. How could I calculate the area of this triangle? And do it two ways. One way would be to multiply base times height, and that would get you the length AC in the argument. Another way would be to get use our trigonometric formula for area, which is 1/2 side, and the sine of the angle in between them. So think of that and see if you can somehow, do that for these 4 different triangles that are implied, and somehow massage out this result. The big result that we're after, of course, is this one right here, right? And if we can get that proved, then the big theorem of the chapter is done. All right, well, we'll see you on Monday for the dramatic conclusion, and hope you all have a nice weekend, and we'll talk on Monday. Take care, everyone.